Hello everyone, welcome. This is the class ECE317, digital signal processing. Last time we studied how to solve system with initial conditions, and today we will keep working on this topic. The way to solve it, right? So we consider today. Let me write down here. It's ECE317. This will be this should be the class on Friday, the 5th week Friday. Right. So for LTI system, we give an input, then we can have an output. So actually now we have several ways. The first is how to describe the system. The system has suppose S has equation. Right? It will be described by equation summation sum a k y of n minus k equal to some bk times x of n minus k. Okay, x is the input, y is the output, and we have equation. Then we can have frequency response e to the j omega equal to, this is a summation a k e to the negative j k omega, and the denominator will be summation bk and e to the negative j k omega. Right, so like this. This is frequency response. Frequency response. And then we can have the output equal to frequency response times the input. Of course, this is in frequency domain. And then we perform by dtft, the inverse of dtft, we can have y of n equal to something, right? So this is we can think this is a kind of a standard way to solve the system. But in this way, we didn't mention anything about the initial condition. So this is we call this a particular solution. A particular solution. Right. And then if you want to find the solution satisfy certain given initial condition, then you have to do two more steps. You need to find this is a 1, then 2. You need to find the homogeneous solution. YH of n. YH of n will be some alpha 1 lambda 1 to the n plus alpha 2 lambda 2 to the n until some alpha, alpha p lambda p to the n. This p is as same as here. This k run from like 0 to p. Here's p. I use p and q for the order. Okay, this is a k run from 0 to q, and y shift. Here's a k shifted by k. K run from 0 to p. Then here's a p. All right. Yeah. And what are these p? What are these lambda 1 to lambda p? Lambda I run from 1 to p. They are roots of just this equation equal to 0. It is summation a k lambda to the m minus k equal to 0. K run from 0 to p. It's this one. You solve these, you get this lambda. Yeah. They are also the poles of H. I will explain this soon. Alright. Yeah. Okay. Then we have YH. Oh, I already have. Yeah, I write here. Alpha I. They are any number, any value. Okay. And the third one, by initial condition, to determine alpha I. Right? We have this. They are any here. By initial condition, then they have special value, not any. Right? Special value. Then we can have y of n will be y the particular solution plus this homogeneous solution with this alpha. Okay. So this is the final answer, right? So whole step to find the final answer. So we need these three. Okay. Then here we have several things we have to mention. So we know the impulse response, right? We have considered the same system as we have del of n. This side will be h of n. It's the impulse response. Right? Impulse response. However, according to this method, this impulse response will depending on the initial condition, right? Different initial condition, you can have different impulse response. Now, which one will be the right impulse response? So I will say like this, like a standard. I say this is standard impulse response. So obtained by DTFT by Fourier transform. Yeah, you can use different way, but just by the Fourier transform way, you obtain that. That is standard way, standard one, right? Standard impulse response. Then with different conditions, then you can have different impulse response. All right. Secondly, what kind of different condition? We say initial condition, but sometimes we have some other requirement. For causal system, that according to the initial condition, h of n equal to 0 for n smaller than 0. Not just the initial condition, it's more than the initial condition. We have a lot of values, all of them. For negative n, they should be 0. Yeah, which is a causal system. And for a stable system, stable, right? Remember what is stable? The BIBO, right? Bounded input should imply bounded output, right? For a stable system, the related initial condition is h of n to summation, right? The summation of h of n, absolute value, will be a finite number. Here for all the n run from negative to positive infinity, all of the n. This is for stable. And sometimes we have another thing is opposite with causal, which is for anti-causal system. For anti-causal system, the related initial condition is, it's anti of these, so that is h of n equal to 0 for n larger than or equal to 0. Just the reverse of this. This one for negative n, 0. Then negative n, right? Negative n. This is already non-negative n. So positive or zeros for this n, h is 0. Okay. So these are some kind of common used condition. And we have similar thing for another kind of input we call step response. Step response. If we use u of n, the unit step as input, go into the system, then this output is a step response. As causal. S is a causal system, then this step response where has value 0 for n negative. Right. We have this. Alright. So sometimes when people say, okay, we have, for example, we have a stable system, then we want to find the impulse response. So how to do it? Okay, you need this condition. Actually, this is just the result from DTFT. So by DTFT, we always get a solution that is stable. That is for stable system. Okay, let's consider example. Let me see. We consider system y of n plus 1.5 y of n minus 1 and plus this one is 0.5 y of n minus 2 equal to x of n. Now consider this system. This is system, right? And we want to find the impulse response. Right? Impulse response. And we have some requirement. The first one we want causal. Second one we want the system is anti-causal. And the third case, it is stable. Okay, suppose we have these three requirements, then what will be the impulse response in each case? The first case, actually no, we can, because we can find the homogeneous solution, we can find the particular solution, they should be same. The only thing different is the condition different, right? So we find the particular solution and homogeneous solution firstly, and then apply the different condition to determine the final answer. Okay, so step 1, we can find the particular solution, right? Firstly, find the particular solution. particular solution. Now impulse response, so input is delta, right? So x of n is delta of n, and then capital X e to the j omega, the Fourier transform of input, it is just 1. And the frequency response, h of e to the j omega equal to 1 over, right? X side we only have x itself, nothing changed, so this is 1. And y side I have 1 plus 1.5 e to the negative j omega plus 0.5. Oh, this is not good. Let me see. I use 1 here. Sorry, I make some change. Just 1. This is 1. And here's a 2.5. Is that good? It's 1 and 2.5. Yeah, 2.5. Use this. 2.5. Okay? It's 2.5. 2.5, and here's a point. No point. Just y of not y. Shifted by 2, so it's e to the negative j2 omega. Alright, we have this. And y equal to h times x. Now it is still x. It's still h, right? X is 1, so just h. This one is just this one. We want to go back. We need a inverse Fourier transform, so we need to try to use the partial fraction. This is 1 plus, I say it's 2 of e to negative j omega times 1 plus half of e to the negative j omega 1. Okay? Yeah, I choose these coefficients just because I can separate them in this way. Okay, then we can have, by partial fraction, it will be some a here and 1 plus 0.5 e to negative j omega, some b here. We try to determine a and b. So here a times 1 and b times 1, there will be the constant term, right? You combine these two together, the numerator will be a times 1 times b as a constant term, and we have a term with e to the j omega, that is half of a and 2 of b. These two numbers to summation, it will be the coefficient before e to the j omega, e to negative j omega. But here no e to negative j omega, right? So this should be 0. Okay, so we use this. It's a plus 4b equal to 0. So a is negative 4b, right? So negative 4b is a negative 4b plus b equal to 1. So negative 3b equal to 1. Negative 3b equal to 1 with negative 1 over 3, and this will be times negative 4, so 4 over 3. So I have a and b, right? So y equal to a, which is 4 over 3, 1 plus 2 e to the negative j omega, and b is negative, is okay, plus the negative 1/3. This is 1 plus 0.5 e to negative j omega. Yeah, we have this one. Alright, then we want to go back. We want to go back to time domain. What is y of n? Let's check the table. Right, we have table, we use the table. Okay, here. We have this term. Sorry. We have this one, right? It's clear? Make it a little bit large. Yeah. It's 1 over 1 minus a something. Go this side is a n to the u of n. But actually here we have a requirement. A, absolute value of a have to be a number smaller than 1. Okay, so we check our result here. We have this, right? So this one, it works. We can have it directly from table. But this one, we need to make some change. We need the coefficient before e to the j omega should be a number smaller than 1. So I have this. I write it in this way. I divide by 2 in both numerator and denominator, so I have 2 over 3 in the numerator, and denominator is divided by 2, so it's 0.5 plus e to the negative j omega, right? They're the same thing. And this is a negative 1/3 over 1 plus 0.5 e to the negative j omega. The second term, I do not need to do anything on it. I already can find the result direct from table. And this one, I times e to the j omega on both numerator and denominator. So this is 2 over 3. This is a 1 plus 0.5 e to the j omega times e to the j omega. Right? I have this. Now 0.5 times e to the j omega. And this one times e to the j omega, they cancel, right? This is negative j omega. You times e to the j omega, so cancel. You get 1. Yeah, I flip the location of these two. I get these two. 2/3, I copy it. And in numerator, I also need e to the j omega. I write it here. And plus negative 1/3, 1 plus 0.5 e to the negative j omega. Alright, now we can use the table. This one, by table, this is DTFT inverse. We can have negative 1/3 times negative 0.5 to the n u of n. We have this. And what it is? Now we check the table. We have this one, but you see this power is a negative j omega. But in our result, here's a positive j omega. Oh, they're too small. We'll make it larger. Here's a e to the j omega, right? E to the j omega. We want this negative j omega. Okay, we have another table. You can see. No, this. Another table is here. This one. X. Not this one. This is negative j omega. Do we have negative j omega? Actually, we can have this. We can use the first one, or let me see. Do I have the formula here? E to the j omega. This one, yeah. Okay, the fourth. E to the, you change omega to be negative omega here. That according to x of negative n. Negative n, right? We use this feature. We use the feature. Okay, let me write it here. I copied. X of n will go to capital X of e to the negative j omega. We have this feature. Okay, and we also need this. Also need these. This is a n u of n according to 1 over 1 minus a e to negative j omega. We have these two. Okay, now let's go back to the notes. Okay. I have these two from the table, and then the thing like this. We have, I write that is y, right? I write let wn equal to negative 0.5 to the n u of n. Actually, this is this one, right? This one by DTFT, it will be capital W e to the j omega equal to 1 plus 0.5 e to the negative j omega as a denominator. Numerator is 1, right? We have this, right? Like this, right? We have this. Then this is a, I say this A, this is a B. Both are coming from table. Okay, by B W of negative n to dt of t, there will be W of e to the negative j omega, right? And W of e to the j omega is this one. The negative j omega is, you just change this omega to be negative omega, right? So equal to 1 over 1 plus 0.5 e to the j omega, negative of negative omega, so here's plus actually. Alright, you see? This is just this part. You got it? So we have W negative n, W of negative n. We get this. And we have one more here. This is what? This is according to shift. Shift, right? E to the j omega according to shift. We check the table. Here I have a table. This. Shift, yeah, second one. Shift. Right? You times e to the something before Fourier transform. That means you do a shift. How many shift? Here's a negative nd, then shift by you minus negative nd, right? Now we have 1 here. No, it's a positive 1, so here's a plus 1. So this is a shifted n go to n plus 1. Right? N go to n plus 1. Here's a minus with nd, here's a minus with nd. Here's 1, here will be plus 1. Okay, let's go again. So this shift, according to shift, we need to replace all n by n plus 1. N plus 1. Okay, so we know what it is. This will be W of negative n, but n replaced by n plus 1. It is. And W is this one. W is this one. Alright? Okay, now we have our result right here. It is W this one, and the coefficient I have 2 over 3, and then W negative 0.5 to the n, but now W this n was replaced by negative n plus 1, so it's a negative n plus 1, and the U of n is a negative n plus 1. Okay, this is this. This is a y of n. This is y of n. Right, y of n. And plus this term is a minus 1/3 negative 0.5 to the n u of n. Now we have this one. Okay, so the final result, we have y of n. This is particular solution. Particular solution is this one. And then homogeneous solution. I have step 1, find the particular solution. Step 1, find the particular solution. Then step 2. Step 2. We want the homogeneous solution. What's a homogeneous solution? Okay, then you look at it here. We have this 2 and this 1/2, right? So these two actually, we say negative 2, negative 0.5 are poles of H. Yeah, for this part. Then you can just use these 2 and negative 2 and negative 0.5 here, add here. That will be alpha 1 times negative 2 to the n plus alpha 2 negative 0.5 to the n for any alpha 1, alpha 2. You can just write it in this way. if you write the h in this, if h is this one, then these two numbers, they will be not y. h is this one. In this example, because x is 1, so y equal to h. In generally, you can only use h, the poles of h. The poles of h are these two numbers. Then here will be the power of these two poles. You can also solve the equation. Right? Solve the equation of lambda. Solve this equation, right? They are the roots of this one. You can also solve this equation, solve the homogeneous equation. But you can also write it directly here. Suppose you already know the poles of frequency response. So we have yh of n is this one. Okay, step 3. Now we have different kind of output. We want to find the causal or anti-causal or stable. So in different case, we need to use different condition for step 3. Okay, so first case, causal, system causal. Then we want h of n equal to 0 for n less than 0, right? Okay, so now h of n, it will be the particular solution plus the homogeneous solution n, and which is the particular solution we just have is this one, 2/3 negative half negative n plus 1, and u of negative n minus 1. Okay, remove the blank. Okay, so then this minus 1/3 negative 0.5 to the n, and u of n. Right, this is a particular solution, and the homogeneous solution is just this, is alpha 1 negative 2 to the n, and alpha 2 negative 0.5 to the n. Alright, and here we have lot, h of n equal to 0 for all of n, and but we only need 2, right? Alpha 1, alpha 2, so we just check 2 to solve it. Consider 2 n in 2, so like negative 1 and h of negative 2. Yeah, we can just consider 2. We will hope it works, because you don't know how about the others. So you need to solve this to find alpha 1, alpha 2, and then check for all the other n's. Do we still have this one? Okay, so I plug in h of negative 1. I plug in all of this here. There will be 2/3 times negative 0.5. N is negative 1. So, okay, negative of 0 is 0, right? And the u of, okay, this is also 0, right? Yeah, this is, maybe this one is more convenient, right? N is negative 1, so this is 0. Negative 0 is 0. Minus 1/3, negative 0.5. N is negative 1, u of negative 1. And plus alpha 1 times negative 2 to the negative 1, and alpha 2 negative 0.5 to the negative 1, and one of these is 0. And h of negative 2, that will be 2/3 negative 0.5. Here's a negative 2. N is negative 2. Is negative of negative 2 plus 1, and u of this is also negative of negative 2 plus 1, and minus 1/3 negative 0.5. N is negative 2, u of negative 2, and plus alpha 1 negative 2 to negative 2, and alpha 2 0.5, negative 0.5 to negative 2, and 1, this is also 0. Alright, now we do some simplify for h negative 1, h of negative 1, the first term, this is 1, this is 1, so this is just 2/3. And okay, this is 0, right? This is 0, so we do not have this term. Then alpha 1 of these, so this is alpha 1 divided by 2, negative 2, right? So it's minus 1/2 alpha 1. And this is divided by negative 0.5 alpha 2 equal to 0. Then h of negative 2, h of negative 2, this is 2/3 negative 0.5. Here is a negative 1, so it's a positive 1, right? Positive 1, so nothing changed. This is just the negative 0.5. And the u of 1, u of 1 is 1, right? And the minus 1/3, this is a negative 2, so divide by square, right? Divide by square of it. Actually this is 1/2, right? Negative 1/2 to the negative 2. So this is just 4, right? It is 4. This is 4 times 4. And oh, this is 0. U of negative 2 is 0. Okay. And the plus this is 0. This is also okay. Both cases, these two are zeros. Then this one. This is alpha 1. This is a negative 2 to the negative 2 power. So there will be 1/4, right? 1/4. 1/4 alpha 1. And this one is 4, right? Square, so this is positive. And the negative 2, you need to reverse it. So this is a 1/2 to the half to the 2. 1/2 turned to be 2 squared is 4. 4 alpha 2 equal to 0. Alright, then we try to solve it. This is just 2, right? 2, and I times 2 in the first. I have 4/3 equal to alpha 1 plus 4 alpha 2. Right? I move this to this side. 4/3. And the second, I times 4. So I have alpha 1 plus 4/16 alpha 2 equal to, this is 0, nothing. I move this to that side. That side is 1/3, right? This is 1/3. This one is just 1. And this 2 times just 1. So 1/3 is 1/3, and I times 4. 1/3 times 4 is 4/3. They are same. Okay, and then get just alpha 2 must be 0, right? Alpha 2 must be 0, and alpha 1 should be 4/3. Is good? Because you see, here you plus 12 more alpha 2. 12 more alpha 2. 12 more alpha 2, but the result is the same. So alpha 2 must be 0. Alpha 2 is 0, and alpha 1 is 4/3. Oh, I don't need alpha 2. Anyway, okay, then we have result. So h of n were equal to, now I just plug in, I have yh is this, and y particular, okay, so h of n, this one, right? Now alpha 1, alpha 2 we already have, so I just plug in alpha 1 and alpha 2. They are particular solution part is the same. Right, particular part is the same. And u of negative n minus 1, and the minus 1/3 negative 0.5 to the n. Okay, here mentioned these two negative, you cannot cancel it, because the n, when n is even number, actually here is a positive, right? If you cancel, then you will miss something. Okay, then u of n, and alpha 1, I just get alpha 1 is what? Oh, alpha 1 is here in my hand. Alpha 1 is here. Alpha 1 is 4/3. So alpha 1 is 4/3 negative 2 to the n. Now we have this one. And can I do more simplify? Yeah, this one. Actually, this one. You see, this one I can rewrite 2/3 times negative 1/2 negative n minus 1 u of negative n minus 1. I just copy these and copy these. Alright, then this is minus 1 here, right? So I can write it. I have a negative 1/2 with power negative 1 times negative 2 to the n, right? Negative 1/2 to the negative n, that it will be negative 2 to the n, and plus times u of negative n minus 1, and the plus 1/3 minus 1/3 negative 0.5 to the n, and u of n plus 4/3 negative 2 to the n. And this one, that will be negative 2. So this is a negative 4/3. Then negative 2 to the n. You see, these two are same, right? And so this is a u of negative n minus 1 plus 1. Oh, this is plus, this is minus. Okay, that's a plus. This is negative. Alright, and minus 1/3 0.5 to the n u of n. And what is this? What is this? If u of negative n minus 1 equal to 1, that is 0. If u of negative n minus 1 is 0, there will be 1. You see? So this is still, you combine together, this is still a u. This is still a u. This one will be always 1. And this one, this u, for positive n, it is 0. For negative n, it is 1. Then you subtract, you go back. Actually, this is just the u of n. U of n. You can check. When n is positive, this is a negative. So this is a 0. It is just 1. When n is negative, then this is a positive minus 1. So maybe positive, maybe 0. So this u will be 1. Negative 1 plus 1. So you get 0. And when n is 0, this is 0. You get a 1. Okay, so totally, this is just the u of n. Alright, so the result is 4/3 negative 2 to the n minus 1/3 half to the n u of n. Alright, you can see what is this u, h of n. H of n, because both we have u of n. I move u of n in the left. They both contain u of n. So all the negative side, they will be 0. And the positive side, you have some value. Okay, this value will go to infinite. Right? We have a 2 power of negative 2. Yeah. But negative side is always 0. It's always 0. And this according to a causal system. It's causal system. Causal. Yeah, it is really causal because our h of n equal to 0. H of for all n smaller than 0. Because this one we have, it is really causal. We find alpha 1 and alpha 2 just by 2 initial condition, right? Just by these 2 initial condition, I find alpha 1, alpha 2, and then the result we know all these, they are 0. So it is really causal. It's really causal. Alright, so this is the first one. And the second one we want the stable. Actually the particular one satisfies summation of h of n smaller than infinity. So that means the particular solution, for the stable case, this is just y particular solution. Yeah, you can show it. With a y particular solution. Actually, the result obtained from Fourier transform will always satisfy that. It's here. You can see it's here. Y particular solution, right? It's this one. It is 2/3 negative 0.5. Here's a negative n plus 1, and the u of negative n plus 1, and minus 1/3 negative 0.5 to the n, and the u of n. For positive n, this one is not 0, but this one is 0, right? Positive n, this is 0. For negative n, this will be this is 0, this is not 0. So these two parts, each give half. So saying like this part given by u of n something, right, times u of n, and this part is a u of negative n plus 1 times something, is this side. And both sides, the value will tend to be smaller and smaller, and to summation still a finite number, smaller and smaller, both positive and negative, yeah, positive and negative, but smaller and smaller, both go to smaller, right? This is a 0.5, half to the n, and this side is also half to the negative n, but n is a negative value, so negative n you get a positive value, right? So it's half with positive power. It's also tend to be smaller and smaller, so look like this. Yeah, this is for stability. And the third case, anti-causal, use initial condition h of, I use a positive side to be 0, so I can use like h of 0 equal to h of 1 equal to 0, and so alpha 1, alpha 2, and we can have some result. Because of time, okay, time is almost done, so you can yeah, if you are interested, you can finish these after class. Actually, we have a homework related to it, so you can also just do the homework. You will have similar problem for the anti-causal. What will happen? Yeah, but that system is different with the system here. All right. Okay. That's all for today. And see you next time.